Welcome to The Explainer. Today we're venturing into some of the most extreme environments in the entire universe. We're talking about regions where the fundamental rules of reality, as we know them, just completely break down.
To kick things off, I want you to imagine you're cruising through deep space. Suddenly, you look out the window and see something that's, well, equal parts terrifying and absolutely magnificent. There's no surface to look at, right? No solid ground to land on. Just a region of pure, absolute darkness surrounded by this blindingly brilliant, glowing ring of superheated matter. You, my friend, are staring down a black hole. And the really crazy part? It isn't just some giant hole in space.
So, what exactly is it? Well, according to Einstein, massive objects curve space-time, and if you compress matter intensely enough into a tiny little region, that curve becomes literally a bottomless pit. The gravity gets so extraordinarily strong that escaping is absolutely impossible. I mean, not even light, which is the fastest thing in the universe, can get out.
And that brings us to the event horizon. This is basically the official boundary of a black hole. But it's absolutely crucial to understand that this is a theoretical threshold in spacetime. It's not a physical brick wall. If you crossed it, you wouldn't, crash into anything. But once you do cross it, the math tells us that every single future-directed path just leads deeper inward. There's literally no route back out.
Now, these things come in vastly different sizes. On one hand, you've got stellar mass black holes. These are born when massive, dying stars totally run out of fuel and just dramatically collapse under their own weight. But then you've got the absolute heavyweights, supermassive black holes. These monsters are millions or even billions of times the mass of our sun. To put that in perspective, our very own Milky Way galaxy has one lurking right at the center called Sagittarius A star.
Section 1. Seeing the unseeable. Right away we hit a bit of a logical paradox, don't we? Because if a black hole traps all light, how on earth do scientists study something that's completely invisible? Well, the trick is, we don't look for the hole itself, we look for the chaos it causes. We can watch stars orbiting some unseen massive object. We look for powerful radiation erupting from accretion disks. That's all that super-fast hot gas falling in. We even use specialized observatories to physically feel gravitational waves when two black holes merge. And amazingly enough, we can now use direct imaging to actually capture the shadow of the black hole against all that glowing gas.
Another spectacular piece of visual proof is something called gravitational lensing. Basically, a black hole's gravity is so enormous that it dramatically curves space-time itself. That means when light from background stars travels near it, the light actually follows those curved paths. The light literally bends. It's wild. This phenomenon makes background galaxies look all distorted, stretched out, or even magnified. It's kind of like looking into the universe's ultimate funhouse mirror.
Okay, let's just hit pause for a second to bust a major sci-fi myth. Black holes do not just roam around the universe sucking everything up like giant, menacing cosmic vacuum cleaners. That's just not how gravity works. Fact check, if our sun magically turned into a black hole of the exact same mass right this very second, Earth wouldn't get sucked in. Our orbit would remain exactly the same. I mean, sure, we'd freeze in the dark, which is a major bummer, but we wouldn't get pulled in. You really only fall in if you get too close.
Section 2. Crossing the event horizon.
So let's take that thought a little further. What if you did get a bit too close? What if you decided to just take the ultimate plunge and fall in? At first, floating there in your spacesuit, nothing really feels out of the ordinary. But as you edge closer, that gravitational field starts doing some incredibly extreme things to your body.
Picture this. If you fall feet first into a smaller black hole, the gravitational pull on your feet is going to be vastly stronger than the pull on your head. This creates what's known as an extreme gravitational gradient. The result? You would undergo a fatal process called spaghettification. And yes, believe it or not, that is the actual highly technical scientific term. Your body gets violently stretched out lengthwise and squished sideways, basically turning you into a cosmic noodle. But here is a totally mind-blowing contrast for you. Counterintuitively, the bigger the black hole, the smoother the initial ride. See, because a supermassive black hole's event horizon is just so unbelievably huge, that gravitational gradient right at the boundary is actually much weaker, meaning you could technically cross into a supermassive black hole without feeling any immediate physical sensation at all, no spaghettification. Which sounds quite peaceful, right? Well, until you remember that once you're inside, escaping is still completely impossible.
Section 3. The final cosmic mystery.
Now this part requires a pretty serious perspective shift. Let's say I'm watching you fall into this black hole from a completely safe distance in my own spaceship.
General relativity tells us that because of extreme gravitational time dilation, your signals get severely delayed. So to me, watching you'd appear to visibly slow down. Your light would become extremely redshifted, meaning it shifts way down the light spectrum, until eventually you just fade away. To my eyes, it would look like you just froze right at the very edge.
And honestly, this just brilliantly illustrates the sheer weirdness of relativity. Because from your own perspective, as you fall, time feels totally normal. You wouldn't freeze at all at the event horizon. You just seamlessly cross that boundary and keep falling inward, deeper and deeper. It's essentially two completely different observers experiencing two entirely different versions of reality.
So that begs the question, is a black hole forever? Well, not quite. Thanks to the brilliant Stephen Hawking, we know that through a quantum effect called Hawking radiation, a black hole actually leaks energy. Over millennia, it slowly loses mass. And over unimaginable eons, we're talking timescales way longer than the universe has even existed, it would theoretically evaporate completely. So they aren't actually immortal, just incredibly long-lived.
Okay, so what exactly is waiting for you at the very bottom of your fall? Well, relativity predicts a singularity, which is a central point of infinite curvature and infinite density. But here's the really crucial takeaway. Physicists don't actually believe this is what physically exists down there. And why is that? Because right at the very center, Einstein's theory of general relativity just completely breaks down. It utterly fails to describe reality under such mind-bendingly extreme conditions.
Which leads us right to the ultimate mystery box. It's one of the most important unsolved problems in all of modern physics. How do gravity and quantum mechanics actually work together? We desperately need a brand new future theory of quantum gravity to figure out what truly lies inside. Black holes aren't just destructive voids. They're essentially the ultimate cosmic laboratories, constantly challenging the very limits of human knowledge.
The universe is hiding some of its absolutely greatest secrets right behind that event horizon. We can measure their gravity, we can watch their glowing accretion disks, we can even photograph their shadows now. But what is truly hiding on the inside? The answer to how our entire universe works on a fundamental level might be sitting right there. But once you cross that boundary, there might be no way to ever bring the answer back out. Just a little something to think about the next time you look up at the night sky.
Thank you so much for joining me for this explainer. I really hope you found this cosmic journey as fascinating as I do.